At its core, machine learning is the science of programming computers so they can learn directly from data, rather than following explicitly programmed rules. Instead of hard-coding a solution, we feed raw information into an algorithm and let it organize itself into a functional model. But learning is not a single uniform process. Inside the field, these algorithms are strictly categorized by the specific amount and type of human supervision they receive while they train. The dividing line in this taxonomy is a concept called ground truth, the explicit labels, answers, or rewards provided directly by a human teacher. To map this out, we use the supervision spectrum. The axes represent the presence of that ground truth, ranging from complete human guidance on one end to zero provided labels on the other. The exact architecture of a machine learning system is entirely downstream of our data. Whether a target variable is fully present, partially present, or completely absent dictates the mathematical objective function we must use. This diagram shows a standard training set for supervised learning. The data includes the desired solutions, called labels. On the right is classification. When the target is a discrete category, like separating spam, the model evaluates a new instance and assigns it to a known class. This scatter plot illustrates regression, used when the target variable is a continuous numeric value. Instead of sorting instances into discrete buckets, the system predicts a specific number on the y-axis, like a car's price, based on given features. The boundary between classification and regression is sometimes blurry. Some algorithms, like logistic regression, are used for classification because they output continuous probabilities, like determining there is a 20% chance an email is spam, to make a final discrete decision. In supervised learning, the system relies on explicit teacher feedback for every single training instance to map input features to a known target. If we completely remove the labels, we enter the domain of unsupervised learning. The training data consists only of raw features, and the algorithm must discover latent structure without a teacher. This visualization shows a raw training set completely devoid of predefined categories. The algorithm's job is clustering, autonomously grouping similar instances together based strictly on their mathematical affinity within the feature space. Here, the dashed lines indicate the boundaries the algorithm has established between these latent groups, entirely on its own, without anyone telling it which group an instance belongs to. This side-by-side view of the iris dataset shows a stark difference. On the left, classification algorithms use labeled species data. On the right, without labels, clustering algorithms evaluate the exact same measurements to detect distinct subclusters natively. Beyond clustering, unsupervised learning also includes dimensionality reduction. This compresses a massive feature space down to a smaller set of dimensions while preserving the underlying structure, serving as a critical optimization step before passing the data to another algorithm. Another unsupervised task is anomaly detection. The system flags rare outliers from the normal probability density, detecting unusual transactions, manufacturing defects, or hidden fraud. When the target variable is removed, the objective function shifts. It moves away from predicting known outcomes and focuses entirely on structural discovery. In practice, assembling a massive dataset is easy, but having human experts manually categorize millions of data points is time-consuming and economically unviable. This plot demonstrates semi-supervised learning. It pairs massive volumes of unlabeled gray dots with a microscopic fraction of known labeled data, the green triangles and yellow squares. The algorithm clusters the data first, then propagates the few known labels outward. This paradigm allows engineers to maintain the high predictive accuracy associated with supervised learning, while slashing the human labor costs required for data preparation. This loop diagram illustrates reinforcement learning, where the algorithm learns by interacting with an environment. The learning system, called an agent, observes its current state, selects a strategy, and performs an action. The agent receives rewards for beneficial actions or penalties for touching the fire. Over time, it updates its internal logic to deduce an optimal policy, defining the best action to maximize long-term reward. This process can result in an optimal policy that defeats human intuition entirely. DeepMind's AlphaGo utilized reinforcement learning to navigate the game of Go, ultimately defeating world champion Ke Jie by executing strategies it learned autonomously. Reinforcement learning shifts the mathematical objective from static pattern recognition in a fixed dataset to dynamic strategic optimization over time. Ultimately, the architecture of any machine learning system is dictated by the constraints and the structure of the available data. Looking again at the supervision spectrum, the full landscape becomes clear. If you have ground truth in your data, you use supervised classification or regression to predict. If you only have raw features, you rely on unsupervised clustering to discover. And if you are operating inside an interactive environment rather than a static spreadsheet, you deploy reinforcement learning to optimize a policy. Mastering this supervision taxonomy is only step one. The next critical engineering decision is evaluating how these models actually ingest all this data, whether it is processed all at once in massive, discrete batches or updated dynamically on the fly.